Hello everyone, this is BADM A724, Quantitative Methods and Business Analytics. This is lecture 3. In this lecture, we'll talk about some concepts and theories in descriptive statistics, describe how data can be presented visually using tools such as dot plots, scatter plots, histogram, polygon, bar chart, line chart, pie chart, and etc. And what are the effective charts? And also what are the deceptive, bad charts or graphs? Visual presentation of the data. There are two kinds of methods of organizing, exploring, and summarizing data, including visual, just using charts and graphs that provide insight into the characteristic of data set without using mathematics. The other way is numerical, using statistics or tables that provides insights into the characteristic of data set using mathematics. Okay? We're going to cover first the visual, and then we'll cover numerical later. Okay? Visual descriptions. Let's begin with univariate data. If you remember, that's a set of n observations on one variable, and consider the following. First is measurement issue. What are the units of measurement? When we measure things, we always have a unit associated with it. For example, if we measure the height of a person, we use foot or inches, and we measure the weight of a person, we use pounds or kilograms. Right? So what are the units? And are the data integer or continuous? A whole number or numbers with decimal places? Right? Are any missing observations? Any concerns with accuracy or sampling methods? This is about measurement. And then the second part is central tendency. Where are the data values concentrated? What seems to be a typical or middle data values? Right? Then about the dispersion. How much variation is there in the data? How spread out are the data values? Are there unusual values, etc.? And the shape of data. Are the data values distributed symmetrically, skewed or sharply skewed, peaked, flat, unimodal or bimodal? Okay? Those are the things that we need to have in visual description of data. Okay? Before we do that, we need to first sort the data. Sorting, for example, in this case, what we have here are the price-earning ratios of some companies, and we sort the data and then summarize in a graphical display. Here are the sorted P ratios, price-earning ratios of some companies. For example, this one here, the first one, the company has a price-earning ratio of 8. That is, its stock price is 8 times that of its earnings per share. And the last company here is 29. So you can see it's hugely different. Okay? We store the data from low to high. Okay? Then we can use a histogram to display the data, and also we can use dot plots. Before computers are readily or widely available, and dot plots was very well used, was very often used tools in presenting data. Okay? In dot plots, you plot each data value as a dot above an appropriate scale, such as this one. Okay? This one shows here the scale from 0 to 70, and each dot represents a company. Right? The range of data shown is the dispersion. Yeah, that's how wide this thing is. Right? The dispersion, and the cluster shows central tendency. Even though the P ratio could be as low as 8 or as high as 69, but most of the P ratios are centered around the data range of between 10 and 30, as we can see. Okay? And then dot plots do not tell much of shape of distribution. Right? We have other ways to show the shapes. Okay? And you can add annotations, text boxes, to call attention to specific features, such as this one here corresponds to Occidental Petroleum, has a very low P ratio, whereas the Roman has a high P ratio. When you compare groups, you can have a stacked dot plots to do that. Compare two or more groups using a common axis scale. In this chart, we're comparing median sales price of single-family homes in the United States. This is the prices in dollars, in thousands of dollars, right? So it's ranging from 100,000, to over $700,000. And this whole country is divided into 4 regions: Central, Northeast, Southeast, and West. If you look at the 4 regions and look at the price levels, price ranges, what do we see here, right? Of course, University of South Carolina, Aiken, we're in the Southeast. This is where we are, okay? And you guys, our MBA students, you may be coming from different part of the country or different part of the world. That's great. Right? So to compare different regions, what do we see here? Where would you find the lowest level of or the cheapest homes? It's probably here, right? Central. In the Midwest or central part of the country, you can find a lot of cheaper houses, right? And in the Southeast, South Carolina, Georgia, and we're not bad. It's not too high, right? Where would you find the most expensive houses? It's probably in the West Coast over here, right? Like in San Francisco or Silicon Valley area, right? And Northeast is also pretty high, maybe in New York or Connecticut, right? Where do we find the largest the dispersion, variations in housing price? West Coast, California, right? Low to high, wide range, right? Whereas in Central, there are expensive homes or middle price, 300,000 level, but they're mostly in this smaller range, right? And Southeast is somewhere in the middle, in between these two, right? So using stacked dot plots, you can compare groups and very nicely by a chart. And for frequency distributions, we can use histograms like this one. These are histograms of heights of black cherry trees, right? The height of trees, between 60 to 90 feet. That's pretty tall, right? And in y-axis, you have the frequency. How many trees you measure in that range? For example, between 60 and 65 feet black cherry trees, there are 3 of them, right? So therefore the height of column here is at 3. And between 65 and 70, also 3. But between 70 and 75, you have 8. Between 75 and 80, you have 10, etc. Right? You can plot that, and this will be a histogram. It shows the frequency distribution. It also shows, the kind of the shape of the distribution, right? You can see it's not exactly, symmetrical, Then for histograms, as we can see in the previous chart, you need to divide those observations into different groups, or we call different bins or different classes, right? So the term bin and bin limits, right? A frequency distribution is a table formed by classifying n data values into k classes or bins, right? Bin limits is the upper limit and lower limits. Define the values to be included in each bin, like between 75 and 85 feet of the height of the tree. Right? The width must be the same across different classes, right? Obviously, in order to compare. Frequencies are the number of observations within each bin. You count how many trees are in each bin. Okay? So you can express data or number as a relative frequency, that's a frequency divided by the total, or by percentage. There's a relative frequency times 100. So you can construct the frequency distribution, but how many groups should we have? Or should we use? You can see that you can divide the total observations, all of the observations into many groups, or more groups, or fewer groups. But exactly how many should we use? Okay? There's some rules you can use. There's a rule proposed by Herbert Sturgis called the Sturgis rule. Okay? He proposed the following rule in constructing a frequency distribution. Basically, for sample size up to 16, he suggests we have 5 bins or 5 classes, right? Divide 16 observations into 5 groups. If you have more than 16 but less than 32, you could have 6 groups. More than 32 but less than 64, you should have 7 groups, etc. Right? And then you have more than 1024, you can have 11 or more bins. But if you have too many bins, it's not too easy or too convenient to display. But for you guys, for your this MBA class, I don't require you to memorize this. For my undergrad student class, or in-house student class, I probably ask them to memorize this. But can you memorize this? I think you can memorize it pretty easily, right? All you have to do is remember the first 2 numbers. You can see here, 16 and 5. And as what you increase number of bins by 1, from 5 to 6, 6 to 7, 7 to 8, etc. And you double the sample size from 16 to 32 to 30 to 64, etc. Right? So all you have to do is remember these 2 numbers, 16 and 5. You're going to remember the Sturgis rule. This is the rule we use to determine the number of bins or classes in frequency distribution. And when you work on the assignments, exercises as a group, you should also use this rule. This example of showing that, for example, between the bin limits of 8 and 12, there are 10 of them. Okay? 12 and 16, 14 of them. And 16 and 20, 17 of them, etc. For a total of 57 observations. Okay? Then from this frequency, you can calculate the relative frequency. That is, for the first one, the first bin or first group, 8 and 12, between 8 and 12, you use number 10 divided by total number 57, you get 0.1754. That's the relative frequency of this bin or this group. Then for the next one, you use 14 divided by 57 to get 0.2456. That's the relative frequency of the second group, etc. Okay? And all these together have to add up to 1. That's 100%, all of them, right? That's old observations. Okay? So, and then you can also calculate the cumulative frequency. That is, you for the first group, 10 is 10, 0, 10. For the second group, to add the cumulative frequency, you count all the numbers in the first group plus the second group. 10 plus 14 gets you 24, right? 10 plus 14 plus 17 get you 41. And then you add all first 4, you get 49. First 5, you get this, and all of them you get 57, which is exactly this one. So that's the cumulative frequency. Okay? Then from the cumulative frequency, you can also calculate the cumulative relative frequency. That is the cumulative frequency divided by total. 10 divided by 57, you get 0.1754, just like this one. And then the cumulative frequency of the first 2 groups, 24 divided by 57 will give you 0.4210. Right? As you can imagine, this is also the sum of these 2 here, right? And then, of course, as you keep adding up more and more, your cumulative frequency will reach 57, the total, and then the cumulative relative frequency will be 100%, or 1.0. Okay. For histogram, that's often used, is a graphical representation of frequency distribution. Y-axis shows the frequency within each bin, and the histogram is also called a bar chart, the same thing. Right? X-axis shows endpoints of each bin. Okay? We can use appropriate technology to construct histograms, such as easily using Excel. Here are 3 histograms for the P ratio data with different bin width. What do they tell you? Right? You can see with 5 bins, 8 bins, or 11 bins. Right? And you can see you have more bins, you show more details, right? More details of that. And the shape and the peak, the tail, the long tail, or the mode, etc. with more bins, more detailed numbers. Okay. As you can see, if you have more bins, you can see there were peaks, or we call them modes, peaks in the chart, in the histogram, here, here, and here, and here, right? And we call that the modal class. A histogram bar that's higher than those on either side is a modal class, or a peak, right? And if there's only one modal class and one peak, we call it unimodal. If there are two modal classes, we call it bimodal. More than two, we call it multimodal classes. Okay? Modal classes may be artifacts of the way bin limits are chosen. As you can see from previous slides, the more bins you choose, the more modal classes can be identified. Shape of the histogram. A histogram suggests the shape of the population. It's influenced by the number of bins and bin limits. And we can see sometimes the peak is symmetrical, but sometimes it's skewed to the left or right. Right? Skewness, or is indicated by the direction of the longer tail of the histogram. We look at the longer tail, right? If the longer tail is to the left, we call it left skewed or negatively skewed. If the longer tail is to the right, is on the right, we call it right skewed or positive skewed. Okay? If both tail area are about the same, we call it symmetrical or symmetric. Like as this chart shows, in this distribution, the longer tail here is skewed to the left, on the left side, we call it skewed left. In this case, longer tails is on the right, we call it skewed right distribution. This one here is symmetrical, right? All first three, they're all unimodal, one modal class, one peak. Right? In this case, there are two peaks, right? Two modal classes, and also skewed left. So it's called bimodal skewed left. This one, bimodal skewed right. And this one is trimodal, three peaks, and symmetrical. Okay? This one here is unimodal right here, and also skewed left. But there are some observations way up here on the left. We call this skewed left with outliers. These are the outliers. Okay? And then there's a skewed right with outliers, and then the symmetrical with the outliers on both sides. Okay? You can also, instead of using bar charts, we can also use line charts like this one here to distribute frequency. This one is called the frequency polygon. Right? The dots represent the frequency, and then we just connect dots. It forms a polygon. We call it frequency polygon, upon P ratio. Yeah. For the cumulative frequency distribution, and it goes up and up and up and up all the way until it reaches 100%. Remember, right? This chart is called the algorithm. Okay? This is a polygon and algorithm. Another type of visual presentation of data is line chart, or the simple line chart is like this one here. Right? This chart shows the monthly basic rate for cable TV between 1975 and 2005 in the about 30-year period. Right? What's happening with the cable rate? How much we pay per month for TV, for cable in your house TV? Right? You can see in 1975, gee, that's cheap. It was only about $6 a month. Nowadays, and this is actually 10 years ago, it's about $40. Of course, nowadays, in 2018, we have more choices, other choices as well. So if you look at the line chart here, just connect the dots, the frequencies or the dollar values for each year, and they will form a line, and we can see the trend here. Between 1975 and 85, the rate is increasing, but not very much. And then it starts to increase faster in an accelerated pace, and up to today. Okay? We can show the trend using line chart. Okay? This is time series data. Okay? And you can also display several variables at once in one chart. This one shows two-scale line chart, showing the cell phone statistics between 95 and 2005. Okay. The red or maroon colored dot line is the average call length of cell phone calls. Okay. The blue dot or line is the average monthly bill for cell phone use. Okay. You can see this is the dollar per month for the bills, and minutes per call on the right hand side is for the length of the call. What's happening here? What does this chart tell us? First, tell us the average monthly bill has been going up, right, from about $35 up to almost $50. That's it is on the rise all the time, right? And the interesting is the average call length is actually dropped from about 3.0 minutes, 3 minutes, down to about 2.5 minutes, 2.3 minutes, and then picking up. Now, why is there a drop here? Right? You may give your own explanation. I've been discussing this with my students. Many of us believe that it could be because of the introduction of text messaging, you know, and therefore there is a drop. Then people start feeling like they need to talk more. Well, that's just one explanation that may is not verified yet. But you can do your own investigation to see if that's the case. Okay. You can also use grid lines. That's line graph. Normally a line graph has no vertical grid lines, but horizontal lines can be added to make it easier to establish the y value. But for between these two, which one is easier to read? You know, it's up to you, but I feel I would go with this one, the one on the right. This is easier, better to read, but this one is just too much, too many lines, too busy. You know, this is clear enough, yet easier on the eye, easy on your eyes. Okay. Log scales. Normally we use arithmetic scales. The distance on the y-axis are proportional to the magnitude of the variable being displayed. But you can also use a logarithmic scales, a ratio scale, using equal distance representing equal ratios. You use a log scale for the vertical axis when the data vary over a wide range, say more than an order of magnitude. If it varies that much, you may want to use log scales. Like the year-end value of somebody's investment portfolio, you know, between 30 and 60 years of age, in a 30-year period, and you can use arithmetic. It shows like this. If you use log scale, it shows like that. Okay. Of course, log scale is only suited for positive data values because you take the log of something, it has to be positive number. Okay. You can also use a bar chart to show data, present data. You can use a plain bar chart, the most common way to display attribute data. Bars represent the categories or attributes. Lengths of bars represent the frequencies. In this case, the tire market share of different brands like Goodyear, Firestone, Michelin, General, Goodrich, Bridgestone, Uniroyal, Continental, and Dunlop. You know, it's when the percentage shows the market share. Goodyear obviously has the highest market share, and just the rest. You can do it this way, vertical or horizontal, whatever you prefer. Which one do you like better? Personally, I like the one on the right better. It seems easier to read. It can show the relative frequency, market share, and better this way. Okay. You can use the 3D or novelty bar charts like this one. The 3D chart, you can use the 3D, the third dimension going into the screen or paper, right? And of course, the third dimension is meaningless. It's just make it look fancier. Okay? Or you can use a pyramid like this one here to show the chart. Okay? You can use a Pareto chart. That's one kind of bar chart that's actually used in quality management. Basically, for this one here, the body shop defects. They find the number of defects for different parts. I guess that's a different part of the body location of your car. You know, like a right central, right door, fender, you know, door, roof, or whatever. You know, and they find the defects. Using Pareto chart, they can quickly identify which parts, which ones are accounting for the most defects, and then they work on the first, say, 2 or first 3 to try to eliminate those defects, to improve quality. So this is a widely used tool in quality management. Okay. You can use the stacked bar chart like this one here. Here are the medical school applications by gender: red for men, blue for women, between 2003 and 2006. The 4 years, you can see the number of applications by 2 medical schools are on the rise overall, and for both men and women, those both are increasing. It seems to be that the red, or the men, are increasing faster, more. That is, more men are applying for medical schools for whatever reasons. Okay. You can use bar charts for time series data. Right? Bar charts can be used for time series data, although it may be harder to compare trends. Here, you can use a chart like this. Right? You can use this line dots to present that, or using a bar chart like this to represent the trend, time series data. Scatter plots. Scatter plots can convey patterns in data pairs that would not be apparent from a table. For example, you have, say, like 2 variables, 2 data pairs, right? Like education and income. We all know that the more education you have, the more lifelong earnings you can expect to garner, to make, right? And then if you plot education, like say X is education, Y is income, you probably see a line like this, the dots like this. Each dot represents a person, an individual person, his or her education and the income. If you form a line like this, you see a data forming a scatter plot like this, we call this strong positive. We call it positive because as X increases, Y increases as well. So it's positive, right? And it's strong, meaning the lines, the dots are actually more coherently stick together to form a line, right? In this case, we call it strong negative, right? They form a line, all right, tightly forming a line, but it goes down. As Y increases, X increases, Y actually decreases. So it's called a strong negative. In this case, we call the weak positive. It's positive, but not as strong, right? This is a weak negative. It's negative, but it is weak. And this one we call it no pattern. And this one we call it nonlinear pattern. It kind of like some other patterns involved. Okay? These are the scatter plots. Tables. We can use tables. That's the simplest form of data display. You can use a compound table. There's a table that contains time series data down the columns and variables across rows. For example, school expenditures. You can arrange of data is in a row and columns to enhance meaning. The data can be viewed by focusing on the time pattern down the column or by comparing the variables across the rows, like this one. School expenditures. You can look at the years, time, down from 1960, every 10 years up to 2000. And you can go across, across columns, you can see the expenditures by type of schools. All schools, there's dollars, the numbers from U.S. Census Bureau, the dollars are in billions of dollars. You can see the elementary and secondary school numbers versus college and universities. And then within each, you can see the private, public, and total. Okay? And pie charts. That's an often abused chart. A pie chart can only convey a general idea of the data. Pie chart should be used to portray data with sum to a total, like a percentage market share example. Right? Pie chart should only have a few slices, maybe 2 or 3 slices, not too many. Okay? Each slice should be labeled with data values or percentiles, like this one here. Where did you get your statistic textbook? Right? This one shows the 54% of people, students, got it from campus bookstore. Right? 3% from non-student, 25% from retail outlet, 18% from the web, like Amazon.com. Okay? You can use a pie chart like this for groups to represent the proportions. The data is from Wall Street Journal, where you can use this bar chart to show whichever you prefer. I would prefer probably this one. It's more straightforward. By just glancing at it, oh, most students got it from bookstore, a lot from web and retail, and then some others. So you get an idea quickly. And you can also use exploded and 3D pie chart that adds some visual impact, but the slices are hard to assess though, right? Like this one here, you can have many slices that's exploded, like the pie with the pieces of pie, kind of exploded out. And you can have this 3D chart like this one, right? Just really like a cheesecake, right? Called exploded 3D pie chart. Excel charts. In Excel you can do a lot of charts, right? You can embellish a lot of charts. You can create a chart in Excel. You can edit it to improve the titles, change the axis scales, add data table, and change colors, patterns, and format the decimals. You can do all kinds of things, and do a radar chart, etc. Right? But there are deceptive charts or graphs that you should not use, and also you need to have the ability to spot them, to distinguish them. Okay? One of them, that is also the errors in making charts. Error number 1 is non-zero origin. If, say, for example, the average length of cell phone calls, if you do not use zero origin, this is what chart looks like. Looks like there's a huge variation here, right? But if you use zero as the origin, then this is what the chart looks like, right? Even there is variation, in the length of a cell phone calls, but the difference is really not that much. So that's first error. Okay? Error 2 is elastic graph proportions. As you can imagine, you can squeeze the chart like this to make the line steeper, or you can stretch the chart, make the line looking, flatter, right? So the aspect ratio is the key. Okay? Normally, keep the aspect ratio, that's the width with height, below 2.0, and not to exaggerate the chart. In Excel, the aspect ratio default is 1.8. Okay? Dramatic title. That's not good, right? You want error number 3. Error number 4, distracting pictures. No good. Right? Authority figures, probably not good, unless the authority really knows something. Right? Here, sorry, I have the missing number 6. It's back in the back. In the next slide. Number 7, missing axis demarcations. You do not demarcate the axis. That's not good. Right? Error 8, missing measurement units or definitions. No good either. Number 6, 3D and rotated graphs. Right? If you look at this chart here, and if you see the medical school applications, you say, oh, the medical school applications soar because you use a 3D and rotated graph. The chart makes the trend appear to dwindle into distance and loom towards you. Right? Therefore, you may have this alarming, shocking title, which is actually deceptive. Okay? The correct chart should be the one on the right. There is increase, but really not that much, dramatic. Okay? Error number 10, complex graphs. You have that many slices of pie or pizza or cheesecake, it's probably not too good. And just too busy, too much information. Okay. Then error 11, gratuitous effects. Avoid too many annoying special effects when using slideshows. Okay. Number 12, estimated data. Estimated data points should be noted when used or avoided if possible. Okay. Vague source may indicate a lost citation, unknown source, or mixed data sources. You need to use complete source citations in your charts. Area trick. As the figure height increases, so does the width. Right? Therefore, distorting the area. right? As the number, the physician salaries when this is clinic, and you can see as the height increases, the width also increases, and that makes the area looking much larger than this one here. Well, when in effect, the true number is in this chart on the right. So that's the correct one. So that's called area trick. So don't use it.